Imagine slicing right through solid titanium using nothing but a beam of light or even just highly pressurized water. Wild, right? Well, welcome to this explainer. Today, we're exploring the fascinating journey from the massive, macro level view of a manufacturing system all the way down to the micro level physics of advanced machining. We're going to unpack exactly how engineers are pushing the absolute boundaries of physics to cut, shape, and ultimately build the future. We have a really clear roadmap for today. We'll start with the holistic manufacturing system boundary, then dive into the principles of advanced machining, cover mechanical material removal processes, explore thermal and electrochemical machining, and finally, wrap up with the latest advances in additive tech. Let's kick things off with Section 1, the holistic manufacturing system boundary, or basically the big picture. Okay, so before we zoom in on how things are cut at a microscopic level, we really need to wrap our heads around the entire life cycle. You see, manufacturing isn't just a guy in a hard hat grinding away at some metal. It's a completely dynamic, interconnected loop. Just think about your smartphone for a second. It starts at the top with customer feedback or some innovative idea, right? That feeds into product design, purchasing, and then into the actual engineering and manufacturing phase. From there, it moves through strict quality checks, goes out into field service, and ultimately loops right back around via waste management. It's a whole ecosystem. But what happens when that critical engineering and manufacturing step hits a hard physical limitation? Well, that brings us to Section 2, Principles of Advanced Machining, and how we break right through those limits. So when we zero in on the manufacturing step of that loop we just talked about, we inevitably hit a wall with traditional methods. The core problem here is that traditional machining relies purely on physical interaction. Your tool must physically outmatch your workpiece. I mean, if you want to cut a diamond, you literally need something harder than a diamond to do it. But advanced machining? It completely throws that rulebook out the window. It uses alternative energy sources instead, kinetic, thermal, electrical, or chemical energy. And because of this shift, the physical hardness of the tool actually doesn't matter anymore. It is a total game changer. Now, we can decode this massive alphabet soup of acronyms by grouping them into 3 distinct energy families. First up is mechanical, which includes things like ultrasonic, abrasive jet, water jet, and abrasive water jet machining. Second is thermal, covering electrical discharge, electron beam, and laser beam machining. And finally, we have electrochemical machining. Let's break these down one by one. Moving right along to Section 3, mechanical material removal processes. This is where we harness the raw power of kinetic energy. Let's start with the mechanical family, where pure kinetic energy does all the heavy lifting. Ultrasonic machining, or USM, is a perfect example of this. Picture a tool vibrating at ultra-high frequencies. Now, the crazy part is, the tool isn't actually cutting the material directly. Instead, that kinetic energy drives tiny, abrasive particles, which are suspended in a slurry right into a brittle workpiece. These millions of microscopic impacts essentially fracture the material away, making it incredibly useful for fragile stuff like glass, ceramics, and quartz. Taking kinetic energy to the absolute extreme, we rely on high-velocity jets. Abrasive jet machining, or AJM, uses high-velocity gas and abrasives for delicate surface cleaning and deburring. Water jet machining, WJM, uses pure, highly pressurized water to cut softer things like rubber, foam, or even food. But when you combine them into abrasive water jet machining, or AWJM, you get an absolute monster. Mixed with tough abrasive particles and fired out at mind-boggling speeds of up to 900 meters per second, AWJM easily slices through incredibly hard metals, composites, and even thick slabs of solid rock. It's heavily utilized in the aerospace and automotive industries for sure. To really understand the mechanics behind these high-velocity jets, we have to look closely at the nozzle geometry. High-pressure water and abrasives are funneled down through a sapphire nozzle into a superfine, concentrated jet. But the key here is the standoff distance. That's the critical gap between the nozzle and the workpiece. As the water jet exits, it inherently diverges. It kind of spreads out. The wider that gap is, the more of that precious kinetic energy is literally lost to the air before it even touches the material. So, to get a perfectly clean cut without any jagged edges, engineers have to master a really delicate balancing act of parametric analysis. By tweaking specific parameters, like, say, increasing the water pressure to boost kinetic energy, slowing down the traverse speed, or decreasing that standoff distance we just talked about, engineers dictate the exact precision, depth, and surface quality. It's literally the difference between a rough industrial chop and a perfectly smooth, flight-ready aerospace component. All right, let's jump into section 4, thermal and electrochemical machining. This is all about extreme heat and dissolution. Moving way beyond physical impact, thermal processes use extreme energy to just outright melt and vaporize material. Electrical discharge machining, or EDM, uses electrical sparks to erode material, which is absolutely perfect for creating complex shapes in hardened steel molds. Electron beam machining, EBM, fires high-speed electrons in a vacuum for incredibly deep, narrow cuts. And laser beam machining, LBM, uses intense light to vaporize material, making it ideal for ultra-precise medical devices. They all follow a pretty violent sequence: generate intense localized heat, melt the material, and vaporize it. The catch, though? All that intense heat can leave behind a heat-affected zone or microscopic cracks right on the surface. But what if you're making a hypercritical component like a jet engine turbine blade, and you simply cannot afford any thermal damage or micro cracks whatsoever? Well, electrochemical machining, or ECM, is your answer. It uses a highly controlled chemical reaction and an electrical current to essentially dissolve the metal away at the atomic level. It completely avoids those thermal and mechanical defects, making it the absolute perfect choice for creating highly complex, contoured geometries inside super tough, heat-resistant alloys. And that brings us to our final stop, Section 5, the latest advances in additive tech. Having thoroughly explored how to subtract material with absolute precision, let's totally flip the script and look at the future, adding material layer by layer. 3D printing is no longer just for prototyping little plastic trinkets, It's enabling incredibly complex structures in the quantum space. Take, for example, custom lattice structures, like wearable 3D printed helmets that are specifically designed to hold hypersensitive quantum sensors for mapping human brainwaves. To quote the researchers who are pushing this exact boundary, "The drive to move quantum technologies from laboratory prototypes to portable, real-world instruments has incentivized miniaturization and intricate three-dimensional forms. Additive manufacturing is basically the ultimate solution here because it offers unparalleled design freedom. It allows us to miniaturize these highly specialized, power-efficient quantum devices so they can actually be deployed out in the real world and not just stuck in a lab." And there's an entire arsenal of techniques making this miniaturization possible today. We have powder bed fusion, which uses lasers to meticulously melt and fuse microscopic metal powders layer by layer to build impossibly complex internal geometries. Then there's vat polymerization, using techniques like two-photon polymerization to sculpt completely custom submicron optics right out of liquid resin. These advanced techniques represent the absolute bleeding edge of that holistic manufacturing boundary we started with at the very beginning of this explainer. So as we master everything from kinetic water jets shattering solid rock, down to atomic-level chemical dissolution, and even quantum-level 3D printing, we realize something pretty profound. The tools we use dictate the boundaries of what is possible to create. We're no longer just shaping materials, we're essentially engineering reality from the ground up. If you found this explainer helpful and want to keep exploring the fascinating frontier of engineering right alongside us, definitely make sure to subscribe to the channel. I'm going to leave you with this final thought. If we can now print structures at the submicron scale to literally map human brainwaves, what impossible technology will advanced manufacturing unlock next? Think about it. See you in the next one.